Hello my dear students, good morning to all. So in my last class I was explaining about what are the different types of electronic spectra we are going to see. So there mainly we are going to classify into 4 general types. So the electronic spectra is classified into 4 general types. So first one is the DD or ligand field spectra. Okay, so DD or ligand field spectra, this is the first type of electronic spectra what we are going to see. So this occurs in the visible region or UV region or infrared region, that is between the wavelengths of 10,000 to 30,000 cm inverse, or in terms of nanometer if we want to say it means 1000 to 300 nanometer. Okay, so in this wavelength, so what and all the electronic transitions that takes place, so that is considered or classified as the DD transition, or it is also called as ligand field spectra. Okay, so here it is depended on 3 major factors. The first one is geometry of the complex, nature of the bonded ligands, oxidation state of the central metal ion. Okay. And next type of electronic spectra is ligand to metal charge transfer bands. So here the charge is going to get transferred from ligand to metal. In the same way, the third type of electronic spectra is metal to ligand charge, which is inverse or vice versa of the second type of electronic spectra. And the last is the intra ligand bands. Okay, so this is these are the 4 major types of electronic spectra. And also I explained about what is meant by selection rules. Means there are certain rules and regulations that especially in the DD transition for the electronic transition to takes place. So we have 2 different selection rules, that is the first one is a spin selection rule. So where the spin selection rule says that, so here only the electronic transitions may occur between the energy states which has same spin multiplicity. So this is the first condition. That means if there is a electronic transition from the lower energy state to higher energy state, definitely so such type of electrons should possess same spin. Okay, so when the transition occurs between the 2 energy states, either lower energy to higher energy, whatever, so the main requirement or condition is that, so these these electrons which are going to transit, they should possess same spin multiplicity. In the same way, orbital selection rule means, so here it talks about the subsidiary quantum number or azimuthal quantum number. Okay. So those electrons or molecules which have center of symmetry and the transitions which do not involve any change in subsidiary quantum number or azimuthal quantum number, so that is delta L, which will be equals to 0 or forbidden, means such a type of transitions are not possible. So these forbidden transitions are also called as a Laporte forbidden transition, because here delta L, that is the change in quantum number, is equals to 0, whereas the transitions which involve a change in the subsidiary quantum number or azimuthal quantum number, suppose if there is a change, that means delta L is equals to 1. So such type of transitions are called as Laporte allowed transitions, right. And the next topic what we discussed was forbidden transition. So even though means for an electronic transition to occur, that means from ground state to excited state the electron is transiting, means so it should possess required characteristics. What are the required characteristics? What we discussed now, just now, that is one is 2 selections rule, first one spin selection rule and orbital selection rule. So that characteristics has to be fulfilled. If it is not fulfilled by the electrons, so such transitions are said to be allowed, or those who does not possess these selection rules, so they are called as forbidden. So allowed transitions involve promotion of electrons without change of spin length. Okay. So such a type of transitions are called as forbidden transition. And also we took an example of electronic transition where 1s to 3p is spin forbidden, but even though by the formation of a new energy state, the lower new state energy which has been formed. So, there is a chance of transition from 1s energy state to 3p energy state, even in the forbidden condition it is partly allowed. So, that is why such a type of transitions are classified as a forbidden transitions. Okay. So, this is where we stopped in my previous class. So, in this session, so let us continue with the relaxation of selection rules or breakdown of selection rules. So, you all know we say that to youngsters like you people, you will say or you will often use this statement, rules are made to break, right, rules are made to break. In the same way, so in my previous class we discussed about selection rules, but in spite of those rules, so there is a relaxation of selection rule or breakdown of selection rules is observed. Why it is like this, and let us take some example and understand what is meant by relaxation of selection rules or breakdown of selection rules. Okay. So, the spin selection rule can be relaxed by the coupling of spin and orbital angular momenta leading to a transition. So, the transition metal complexes which do not give DD transition, so also exhibit color due to the relaxation rules. So, here we should concentrate on transition metal complexes. The topic itself is the electronic spectra of transition metal complexes. So, all these transition metal complexes, they have got their own characteristic color. So, that color is observed, or if we are seeing that color means, so they in that particular wavelength, so our eye is capable to observe the light. Okay. So, that wavelength what we distinguish as in the visible region, Vib-Gayar, we call it as Vib-Gayar. So, different wavelengths will represent different colors. So, starting from violet to red. Okay. So, that is how we are going to understand the electronic spectrum. So, I need not to explain much deeper about that, you all know about that. Vib-Gayar, we call it as 7 colors. So, it ranges between different wavelengths. At that particular wavelength, when that reaches our eye, we are going to detect it or say, so this is red color, this is green color, this is violet color. Okay. So, this is what actually the electronic spectrum means. So, here the transition metal complexes which do not give DD transition, such a type of metal complexes also exhibit color due to the relaxation of selection rules. Okay. So, now we will see mainly two concepts are there in this relaxation of selection rule. What is that? We will see one by one. So, the first one is when transition metal complex ion does not has perfect octahedral structure. Okay. So, usually as I said while explaining about the DD transition, the first type of electronic spectra, there I said that is so here in DD electronic transition, the energy gap between T2G and EG orbitals depends on 3 factors. In that, first one is geometry of the complex. So, here see, we are understanding the geometry of the complex here. Suppose if the transition metal complex ion, it does not contain perfectly octahedral structure or slightly distorted structure, then the center of symmetry is distorted. Okay. So, you just imagine a structure. Suppose if okay, just imagine the complex structure, there will be a central metal atom, okay, or a central metal element molecule. So, to which the ligands will be attached. So, those ligands will be attached in a geometry, that means it should have specific distance, bond length. Okay. So, such a type of perfect octahedral structures will be there in the transition metal complexes. So, sometimes what happens is such geometry will not be absorbed at that time. So, the structure will be distorted. Distorted means changed, it will not be a similar distance between the ligands and the metal atoms. Okay. At this stage, the symmetry is also distorted. So, in such cases mixing of d and p orbitals may occur. Here no DD transition is observed. there is a chances when the symmetry is lost, then there is a mixing of d and p orbitals. So, instead of dd transitions, transitions are due to d and p levels. Okay. So, this is the first concept in relaxation of selection rules. So, what happens when the transition between d and p levels takes place, energy level takes place is, so the intensity of such transitions are weak in the range of 20 to 50 epsilon. For example, so complexes like pentamine cobalt 3 chloride, so which have irregular octahedral structure and do not possess a center of symmetry are also colored. And okay, so this has got irregular octahedral structure and it does not possess a center of symmetry, even though due to the transition between d and p energy levels. So, such complexes like pentamine cobalt 3 chloride, so they are colored. Okay. So, the mixing of d and p orbitals does not occur in perfectly octahedral complexes which have a center of symmetry, for example, hexamine cobalt 3. So, the tetrahedral complexes such as manganese chloride or manganese bromide, which do not possess a center of symmetry, have intense color. Okay. So, these are some of the examples which also possess color, even though it does not possess a center of symmetry. Okay. So, those complexes which are formed by manganese chloride or manganese bromide, so they do not possess center of symmetry, but they have intense color. Okay. So, this is the first type of relaxation of selection rules what we have to observe. And the second is a complex which has a perfect octahedral structure. Okay. So, here the first one is which does not has a perfect octahedral structure. Now, we will see, suppose if the complex has got perfect octahedral structure. So, what happens, how the color is going to be absorbed and what is the concept involved in this, what type of coupling is going to takes place in such complexes. Okay. A complex say for example manganese hexahydrate complex. So, this manganese hexahydrate complex is very interesting. So, it has got 5 unpaired electrons in the outermost shell, even though if it is having 5 unpaired electrons. So, it possesses spin multiplicity which is forbidden. Okay. It is forbidden because since it has got 5 unpaired electrons, definitely the spin multiplicity of this particular complex will be not similar or same, but still we are seeing a pale pink color due to the vibronic coupling. Okay. So, what is meant by vibronic coupling? So, vibronic coupling is a absorption spectrum in which we are going to see the electronic transition which is occurred due to vibronically allowed transition. So, here the vibrational and electronic coupling together, which is called as vibronic coupling, will remove the center of symmetry. So, if a forbidden band lies near an allowed band, so due to the permitted transitions, so mixing of fully allowed and forbidden energy states due to the vibronic coupling gives intense absorption. So, such a type of intensity or increase in the intensity of the color, so it is called as intensity stealing, and it depends on the energy difference between two states, between two energy states. Okay. So, the two energy states are, so T2G and EG. So, these are the two energy states which we are going to see. So, the energy gap or the energy difference between these two states is called as intensity stealing, and a well known example is, as I said, manganese hexahydrate complex. So, in which all the transitions are spin multiplicity forbidden and Laporte forbidden are pale pink in color due to vibronic coupling. Okay. So, these are the two relaxation of selection rules what we are going to see in electronic spectra of transition metal complexes. Okay. And next is Orgel diagram or Orgel energy level diagram for D1 and D9 system. So, what are these Orgel energy level diagram? So, these are used for the interpretation of spin allowed absorption bands of spectra of crystal field or DD origin in the electronic spectra of octahedral and tetrahedral metal complexes. Okay. So, these are the diagrams which represents the interpretation of spin allowed absorption bands. Okay. That too especially when the electronic transition takes place in a weak field, it is very difficult, not very difficult, it is quite difficult for us to understand the absorption bands of the spectra. So, in such cases we are going to represent them by using a diagram which is called as Orgel energy diagram. Okay. So, the spin allowed transition occur between two energy levels which have same spin multiplicity. So, this is the first selection rule what we saw, we already discussed about this, that is the energy the two energy states like how I said T2G and EG energy state. So, for the electronic transition to takes place from T2G state to EG state or EG state to T2G state. So, the criteria or condition is that, so it should have same spin multiplicity. So, the electronic transition occurs from ground state energy level. Usually the electronic transition will occur from ground state energy level. So, the various aspects of energy levels of DN system may be presented in a diagram which is called as a Orgel diagram. Okay. So, the energy level diagram of spin allowed electronic transitions showing the splitting of only the ground term as a function of strength of octahedral or tetrahedral field is called as Orgel diagram. So, if at all a question is asked what is Orgel diagram or define Orgel diagram, so then you have to answer that. So, the energy level diagram of spin allowed electronic transition showing the splitting of only the ground term as a function of strength of octahedral or tetrahedral field is called as Orgel diagram. Okay. So, now we will take one example, Orgel diagram for D1 system in octahedral field. Okay. So, this diagram, so this explains about the Orgel diagram for D1 system. Okay. So, D1 system and this is for D2 or sorry D9 system. So, this is for D1 system and this is for D9 system. Okay. So, observe these two Orgel diagrams. So, what you are going to understand from these two? So, here if you concentrate and observe, the term symbols for ground and excited states are reversed. Okay. So, here you see, so this is the ground state here. So, in this DD transitions or the transition metal complexes, so they will possess or it will have only one energy term, that is 2D. So, 2D is the only energy term which is there for D1 or D9 system. Okay. So, here also 2D. So, 2D is the only one energy term. So, here if you see, so these are the two different energy states, so one is 2T2G and another one is 2EG. Okay. So, here if you observe, so this is for D9 system. So, here the energy states are reversed. See here this is the ground state, it has been reversed, that means so here the ground state is 2E2G. That means the difference between the Orgel diagram of D1 system in octahedral field and Orgel diagram of D9 system is, so here the term symbols for ground and excited states are reversed. Okay. So, that is why here we have 2T 2G here in the ground state, whereas in D9 system it is in the excited state. Okay. And next let us discuss electronic spectra of titanium hexahydrate complex. So, the complex ion titanium hexahydrate contains only one d electron in the ground state. It has got only one d electron. So, that electron should undergo electronic transitions. It will occupy the T2G orbital. So, initially the one electron which is present in the titanium hexahydrate complex, so that one electron will occupy the ground state. that too especially T2G orbital. So, on excitation what happens when it absorbs a radiation, when it absorbs a light energy, it excites and it will absorb radiation and move into EG orbital. Okay. So, this is EG orbital. So, these two are the Orgel diagrams, so which represents the electronic spectrum or absorption spectrum of titanium hexahydrate, where the only one electron which is present in the ground state, so which that will occupy T2G orbital, and thereby after absorption of radiation it will move into the one of the EG orbital. Okay. So, let us understand it in deep. So, as I said, so this complex, transition metal complex, it has only one energy term, that is 2D. 2D is the only one energy term. So, when titanium is surrounded by octahedrally by 6 water molecules, so this electron enters 2Tg level. Okay. So, now imagine the structure of the complex. Titanium is the central metal atom. So, this titanium will be surrounded by, since there are 6 hydrated molecules, that is water molecules, 6 water molecules are there. Titanium will be in the center and it will be surrounded by 6 water molecules. At this condition, so the one electron which is present in the titanium, so that enters T2G level. So, that is why it has been shown in the ground state. So, the ground state configuration of titanium hexahydrate is a T2G1. So, it is called as T2G1. Whereas, on absorption of radiation of frequency, let me call it as delta E, means the change in energy or the absorption energy, absorption of radiation, which will be equal to h nu, the electron gets promoted to one of the EG orbital. So, this is the EG orbital. From here, from ground state to excited state, the electron is going to be transisted. The energy gap delta E depends on the strength of the octahedral electrostatic crystal field potential, which is generated by 6 water molecules. Okay. So, the 6 water molecules which are surrounded by the titanium, so it will generate a electrostatic crystal field potential. There will be a attraction. Okay. The titanium will pull all the 6 water molecules which has been coordinated with it with the electrostatic force of attraction, which is called as crystal field potential energy. So, the absorption spectrum of titanium hexahydrate shows a broad band corresponding to the wavelength of 5000 angstrom or frequency of 20,400 centimeter inverse. Okay. So, this is a mathematical data. So, they have performed the experiment, they have studied in deep that titanium hexahydrate complexes, and they have given. So, this is just for your knowledge. So, this absorption spectra of titanium hexahydrate shows broad band of spectrum in between the wavelength of 5000 angstrom, or in terms of frequency, if I want to say it, so it will be around 20,400 centimeter inverse. Okay. How much energy is measured here is so the energy change is 57.15 kilocalories per mole. So, which must be a delta value for this complex. Okay. So, for this complex 57.15 kilocalories of energy has been measured in terms of delta E. So, light of wavelength 5000 angstrom is green. So, that is why so this titanium complex will appear in green color. If such a light is absorbed, the transmitted light appears in purple color. Okay. So, the absorption band at 20,400 centimeter inverse of crystal field origin can therefore be assigned as so 2T 2G to 2EG. Okay. So, this is the transition. If we want to represent this titanium hexahydrate electronic spectra in terms of term symbols, so it can be written as 2T 2G to 2 Eg. Okay, so this is how we are going to understand the electronic spectra of titanium hexahydrate. Okay, so another electronic spectra what we have to observe here is copper or cuprous hexahydrate complex. So this the first one is a example of a D1 system, and this is an example of D9 system or D9 configuration. Okay. So, the complex has D9 configuration in the ground state. So, this complex, the spectroscopic ground term is 2D. So, same. So, for these both spectroscopic ground term is 2D only. So, here, so this is an example where we can see the term symbols for ground and excited states are reversed. So, one is for D1 system and another one is, so this is an example of D9 system. So, here you make the observation that, so here, so 2Tg which is in the ground state will be in the excited state in case of cuprous hexahydrate complex. Okay. So, the spectroscopic ground term is 2D which is similar to D1 configuration. So, the one unpaired electron which is present in the Eg level is transferred. So, here the unpaired electron which is present in D9 system, that will enter to the lower energy state, and once after absorbing the radiation energy, so it will excite from Eg level to T2G level. Okay. So, this is what the observation what we have to do. So, this is the difference between the titanium hexahydrate and cuprous hexahydrate complex. Okay. So, one is the example of D1 configuration and another one is the example of D9 configuration. In both only one unpaired electron is present, whereas in titanium hexahydrate, so that one unpaired electron it will enter to 2Tg energy state, that will be the ground state, whereas in cuprous hexahydrate, so Eg will be the ground state and it will transfer to Tg level. Okay. So, the energy level diagram for D9 is therefore the reverse of that for the D1 configuration. Okay. So, if you observe clearly, so these two energy level diagrams or Orgel diagrams, you will understand it. So, for this purpose the absorption band is assigned to 2 Eg to 2 Tg in case of cuprous hexahydrate complex, and the broad band at 12,000 centimeter inverse is due to the large distortions from octahedral symmetry. Okay. So, this complex has got octahedral symmetry, and why we are going to get a broad band, that is because of the large distortions which we are going to observe. Okay. So, this completes this unit, that is electronic spectra of transition metal complexes. So, if you have any doubt, you can ask me when you come to the college, or you can also clarify that in the Google Meet class or in any way. Okay. Thank you dear students. So, in my next class we will start with the new chapter. Okay. Thank you.